So let's get started with the first talk. It's multi-party replicated secret sharing over a ring with applications to privacy-preserving machine learning. The talk is being given by Alessandro Baccarini. Take it away, Alessandro.
Thank you. I'm Alessandro. I'm from the University of Buffalo. I'm actually here with one of my co-authors and advisor, Dr. Marina Balentin. She's going to be giving a talk later on, so you'll be hearing from her soon. So to introduce us, this segment of the conference is pretty condensed with multi-party computation, but just by show of hands, does anyone not know what secure multi-party computation is? So do I even need to discuss the slide that I painfully put together with these kind stock images? No? All right, well, anyways, okay. So secure multi-party computation basically involves multiple participants jointly evaluating some arbitrary function or performing computation on secret inputs without disclosing any information about their inputs themselves, and the only thing that gets revealed is the output. So no information is leaked throughout the execution of the entire computation. Functionally, it replaces the need for a trusted third party. And just to add some notation, we have n parties with a corruption threshold of t. So at most, t parties can be corrupted or collude in order to, at that or lower, and the protocol security or specifications will still hold. And there's a wide breadth of applications, anything that deals with personally identifiable information, health records, a lot of applications into machine learning, as the name of the paper and talk implies. And that's part of what I'm going to get into later today. So in terms of actual techniques, I'm going to highlight secret sharing. So secure multi-party computation is a broad field, but as a subfield is secret sharing. And the most ubiquitous, arguably, technique for secret sharing is Shamir secret sharing, which typically involves computation over some field modulo a prime. Now, some of the inherent difficulties associated with that is if you are doing any work over a field, you're going to require some frequent modular reduction, and you can't work with these large values that Shamir secret sharing demands with inherent or not inherent, built-in types that most processors have. So you typically need to use an external library like GMP to use long data types. But that is where replicated secret sharing comes in over a ring. So some of the benefits of a ring computation is that it is very efficient and arguably easier to conceptualize than Shamir secret sharing, which you split up shares based off of polynomial evaluation and perform Lagrange interpolation. You don't have to do that for replicated secret sharing. And there is a good performance to security trade-off, which plays into the security setting that we consider, which is the semi-honest, honest majority setting. So the corruption threshold is less than half of the total number of participants. And the main benefit also is we can use built-in types, 32 and 64-bit integers, and it's very easy to implement. So the main contributions of our paper were to develop a framework based on replicated secret sharing for any number of parties. So typically, any prior implementations of that use replicated secret sharing limited their scope to 3 parties, which is the most common setting. But we expand that to any parties and over an arbitrary ring for the fundamentals and building block protocols. That can be over any ring. But for some of the composite protocols that we'll discuss, they only work over the ring Z2K. Second major component that I'm going to talk about are quantized neural networks. And we introduced or developed a optimization that allows us to reduce the overall ring size over by a factor of 2 compared to the current state of the art. And then we did a whole bunch of benchmarks against the field versions and the current state of the art, such as MP speeds. So the basic introduction to replicated secret sharing is that instead of where you have n parties for Shamir secret sharing, each party is entitled to a single share, you split up a secret into n choose t shares, and you distribute those n choose t shares to you distribute n minus 1 choose T shares to each party, defined by some specific access structure. So parties who are entitled to shares versus shares that are entitled to a specific party versus shares that you don't have access to. So for an example, if you have 5 parties, there's a total number of 10 shares, of which each party gets 6. Now, something that you may notice is that this may scale pretty significantly for even more parties, so 7, 9 parties. The total number of shares grows very quickly, and the overall performance is dominated by the communication. That's something to keep in mind. So any notation where we use x with the square brackets of k denotes a secret shared integer or value over the ring z to k. So for this framework, we have 3 main components. We have our building blocks, so any fundamental operations like multiplication, addition, reconstruction. So you have a value that is secret shared. You want to be able to reconstruct it and reveal it as part of the second and third categories, which are random bit generation and composite protocols. All of those building blocks are compatible with any ring that you choose to do your computation over. Another fundamental component required for the third stage is random bit generation. So previously, the standard was to generate a single random bit shared over Z2K, and if you need to get individual bits of a longer value, you'd have to generate multiple random bits in parallel, which doesn't scale well with the batch size or the input. A couple years ago, the Edibit framework was developed and introduced a very attractive alternative, of which we use and compare both of those implementations in our composite protocols. So most significant bit, most prominently used for comparisons, very widely used for any application you can think of. If you want to compare whether 2 values are, which one is greater, you're going to be using most significant bit. Second of which is truncation, where you want to divide a value by a power of 2, very useful for reducing the size of your values for quantization, which we'll talk about in a minute. And then lastly, conversion is if you are working on in a specific ring size, you need to expand it for whatever accuracy or performance needs that the program you're trying to implement dictates. That would be of use. So, as I alluded to, one of the main benchmarks we addressed was quantized neural networks. So if you want to think of a quantized neural network, it's just a smaller version of a full-size neural network where you have real valued inputs for your weights, biases, and whatnot. They get quantized down to an 8-bit range. In that procedure, each of these these parameters and inputs to the computation have associated scales and 0 points, where you have your traditional a arbitrary weight or dot product or a layer computation gets converted to something like this, where each of these parameters have associated 0 points, and you have to do this multiplication by the scaling factors for a given layer, and you add the 0 point, and that's the analog between the two. We got one more slide actually. By construction, these values are guaranteed to be within 0 to 255, but just to ensure that everything operates correctly, you have to clamp the values to that range. And certain activation functions, which are inherent to any neural network, specifically ReLU6, that can be done for free by incorporating or by modifying the layer parameters to effectively achieve that outcome without needing to do any additional operations. So a couple years ago, the first landmark paper that dealt with quantization and secure multi-party computation, their procedure was to do a sort of fixed point multiplication, which followed the standard for TensorFlow to compute this product of the dot product and the scales. You do a fixed point multiplication and then a truncation to get everything back into the expected range, and then you would perform the clamping operation. Now, the problem associated with that is that this requires a you have to use a larger ring size to accommodate for the precision that is required by the construction. So they had to use a ring size of 72 bits and do a 63-bit truncation to ensure that the fixed point multiplication was correct. What we ended up doing was we did some sort of algebraic manipulation to, instead of having to do this large truncation, you can move around or do some, like I said, rearranging, algebraic wizardry to get it in such a way that the fixed point multiplication is now part of the bounds of which you are clamping your result to. So you won't have to do that fixed point multiplication. This will get updated and becomes part of the model itself. There's no impact on security, and again, there's no impact on accuracy because this is just pure algebraic manipulation. You won't need to worry about anything happening with that. But as a consequence of this, the values will grow as you evaluate more and more layers. But that's easily remedied by performing a truncation back to a reasonable range, so around the 8-bit range to maintain the expected accuracy. But the trade-off is that you can reduce the overall ring size by a factor of 2 by doing this method. So again, everything else stays the same. The model parameters have there's an additional model parameter, but there's no impact on security or leakage with this technique. So quick summary of the results. Replicated secret sharing, there's a lot of attractive options provided by replicated secret sharing. So especially for 3, 5, and 7 parties, those are benchmarks that are contained within the paper, as well as we did a comparison of the random bit versus edit-bit, both of which outperform the field-based variant quite significantly. And our performance is on par with the current 3-party standard and state-of-the-art for quantized neural networks. Our implementation, albeit equivalent to MP speeds, which is highly optimized for larger batches, it performed, it matched. And future work is just to integrate it to the Pico compiler and introduce floating point compatibility to replicated secret sharing, which is currently missing in the literature. And I'd be happy to take any and all of your questions. Thank you.
Quick reminder to please ask your questions on the Zulip. In the Zulip, there's a chat room called Session 2A, and there's a thread for each talk. Right now, there are no questions, so I will ask one. Thank you very much, Alessandro, for the great talk. I was wondering, this construction seems to be optimized for privacy-preserving machine learning use cases. Were there any other use cases that you envisaged that would be, this construction would produce performance optimizations in as well?
So the construction being replicated secret sharing or that quantization improvement?
The quantization improvement.
So the quantization improvement is beneficial for secret sharing because of dealing with truncations and having to have a larger ring size. If you're just performing inference on a quantized neural network on your local device, and you're not concerned with privacy preserving, it doesn't really make much sense because, the existing frameworks like TensorFlow or TensorFlow, for example, they already have everything pretty well optimized for, specific hardware needs and whatever's built-in capabilities of a processor. So I wouldn't see that this, would be beneficial beyond secure multi-party computation, but that's what it's specific for.
All right. Well, let's thank our speaker again.
Thank you.